Today we are going to talk about implicit differentiation. This is section 2.5 in your book. The first thing I should do is talk about what an implicit equation is. So if I have y equals x squared sine x, or y equals x to the fourth over cosine x plus 1, these are called explicit curves. I give you the x value and you can plug it through and get the y value. It's in a form y equals. An implicit curve would be something like x squared plus 2xy minus y cubed equals 8. One that is not in terms of like a y equals. And in this case, it would be difficult or impossible, probably just difficult, to solve for y explicitly in terms of y equals. You guys know how to take the derivatives of these kinds of equations, but we don't yet know how to take the derivative of this. Well, you might actually be able to figure it out. It's really just a little bit of chain rule. But let's just go straight into, actually, I have a question for you, and I want you to answer this in your head. What does it mean if dy dx is equal to 0? What is dy dx equal to 0? What does that mean? If a derivative was equal to 0. Well, let me just draw a little curve, right? Well, it could be that spot, or that spot, or that spot. All of those spots have tangent lines that are horizontal. So what does dy dx equals 0 mean? It means that there is a flat slope. Okay, so let's go ahead and look at an implicit curve that you should all be familiar with, and that we can do. That is a good example for me to start with to show you what implicit differentiation is and how it can tell us useful things that regular derivatives cannot tell us. So it is the unit circle. X squared plus y squared equals 1. You should know that that is the unit circle. You should know circle equations from like algebra 2 and stuff like that. If you don't, that's okay. This is x squared plus y squared is 1. It's the unit circle. Boop, boop, whoop. This length is always 1. The x distance, here I'll do it in green, plus the y distance in orange. Well, those guys, there's a right angle right here. So, because of Pythagorean theorem, the x value squared plus the y value squared is the hypotenuse squared, and that will always be 1. So if I do the equation x squared plus y squared equals 1, it gives me the equation of a circle of radius 1 because of Pythagorean theorem. Anyway, so I'm gonna write something. I'm gonna hit pause, write something, and well, here I want to know what is dy dx equal to. Okay, I'm gonna hit pause and then write it, and you'll see the long way to get it, and then I'll show you the good short way. Okay, so I've got x squared plus y squared is 1. I can move the x squared over. I can square root both sides. Now, there's actually an error in this, but I wanted to leave it off because of what I get below. But it should be plus or minus in this case. Why is it plus or minus? Because there's a top half and a bottom half of this thing. If I have y equals, think back, you probably did a conics project at some point. But then I can take the derivative. I get negative 2x, that's chain rule, 1 over 2 root of, and this, and then it simplifies to this thing. Now, this is kind of annoying because I have lots of steps, and there's all these 2's that I can forget, and the negatives, and this is not always as useful as a form of the equation. So I'm going to show you how to do this, how to find the derivative, the slope of the unit circle, given using implicit differentiation. So first thing I'm going to do is write it a little bit differently. I'm going to write it as x squared plus y bracketed squared equals 1. Why do I do this? Because when we learned how to take the derivative of sine squared, x, we wrote it as bracket sine x squared, and that helped us see the chain rule. what I want you to do is see that, well, the first, I'm going to write d over dx. Remember, d over dx with an arrow, it's like a verb, right? It means take the derivative with respect to x. If I did d over dt, it would mean take the derivative with respect to t, probably time. So derivative of the first term with respect to x is easy. It's just power rule 2x. Plus, this is why I bracket this thing. So I'm deriving this guy with respect to x. So how do I do that? Well, I'm gonna write it a little bit backwards from how we sometimes do it, but that's okay. I'm gonna write 2. What's the derivative of squared? Well, it is 2 to the first power. I'm not gonna write that 1 because then it looks like prime, right? But that is 2 to the first power times, what is the It is the y. It slides in here. But remember, when I do chain rule like that, I need to do the derivative of the innards. So what is the derivative of y with respect to x? Well, that's exactly what we're looking for, times dy dx. It's just chain rule. Equals, what do I get on the right side? What's the derivative of 1? It is 0. So divide by 2 everywhere. I get, and simplify, I get x plus y times dy dx equals 0. From there, I move the x over, and that gives me, well, I guess I'll show all the steps. Y times dy dx equals negative x. And then I can divide by y, and I get that dy dx is equal to negative x over y. Now, you may say, that's more lines than this. Well, it is, but this is a more simple version, right? This is a simpler equation than this thing. 2, there are, I could only do this because I was able to solve for y. And there are lots of these equations where solving for y is either annoying or impossible. So having this technique here allows me to take the derivative of something where I can't get it into a y equals form. The third thing you might say is, yo, this and that, they're not the same thing. But I would argue to you that this is the same as that, because what equation did this come from? X squared plus y squared is 1. If you look at actually this line right here, oops, that line was the one where I square rooted, right? So take a look, root 1 minus x squared, that's root 1 minus x squared. Well, it's just y, so it's negative x over y. And having it in this form can make it more simple for me to recognize some things. So in order to convince you of that, I'm going to show you a couple spots where this equation makes sense. So let's look at the unit circle here. What's true right here about the tangent line? And what's true right here about the tangent line at those two spots? Well, that's why I asked you this question up top, right? Oh, the tangent line is horizontal. Well, what is the x-coordinate at those two spots? That's the side-to-side coordinate. It's 0. Well, dy dx is equal to negative x over y. So I would argue that dy dx, I'm going to throw new notation at you. If I put a vertical bar and then I write x equals 0, that means evaluated at x equals 0. Well, that is, what happens if I put x equals 0 in here? Well, I get a fraction with a 0 in the top. So it gives me 0, right? What does that mean? Horizontal slope. Okay, cool. That makes sense. Let's look at another one. So let me go and draw the unit circle. What's true here and here? Well, the tangent lines at those two spots are vertical. And what is the y-coordinate there? The y-coordinate for each of those is 0. Here, the x-coordinate is 1, and sorry, on this side the x-coordinate is 1, and on this side the x-coordinate is negative 1. What I want you to notice is that dy dx evaluated when y is equal to 0 gives me some number. I will say it's important to recognize that the number is not 0, but in this case it doesn't matter because that y is the the top of the fraction is either going to be 1 or negative 1 over 0, right? What I'm saying, this equation evaluates to a number over 0. I could put the negative there. It doesn't matter. When I plug in a y equals 0, well, I can't have that. That breaks math, having a 0 in the denominator. But what does it go to? What does the fraction go to as the denominator goes to 0? It goes to infinity. And what's the slope of a line that's vertical, that's up and down? What is the rise over the run? It is infinite. So it should make sense that when I get a 0 in the denominator, 0 in denominator, that gives me a vertical tangent line. And that's one thing that we often look for in these questions. So the last one I'm going to talk about, the last place where this makes sense, dy dx equals negative y over x. Did I flip that? I did. Negative x over y is at the 45-degree angle on the unit circle, right? So if this was pi over 4, look, in your head, what's the slope of this line right here? What is the m on that line? You should be able to intuitively figure out what the slope of the tangent line at a 45-degree angle would be. Well, it is negative 1. How does that make sense? Well, on the unit circle, you should know this is root 2 over 2, comma, root 2 over 2. This is the x coordinate. This is the y coordinate. So when I take dy dx and evaluate it at root 2 over 2, comma, root 2 over 2, well, the top and the bottom are both the same thing, so I'm not going to write them again. It just gives me negative 1 because they cancel with each other. And that matches with the idea of what this slope would be. Hopefully, the idea of implicit differentiation makes sense. It's nothing but chain rule on this kind of thing right here. And hopefully, all of the ideas around horizontal slopes, vertical slopes, and then the fact that this makes sense is sort of making sense for you guys. I will do another video or 2 or 3 or whatever it takes to do several more examples.